All right, today we're going to enter lecture 2 of Corona Watch, and we're going to talk about how we can treat spin for those wonderful excited states we introduced last time. So, just as a reminder for the Pauli principle, we can't have two electrons with the same spin in the same location. If they're going to occupy the same location, they have to have opposite spins. Now, let's go ahead and start by examining our good old friend, the helium ground state wave function. So if I've got a helium ground state, I've got two electrons, one in the 1s orbital and the other one also in the 1s orbital. Now, because they're occupying the same exact orbitals and my wave function has to be antisymmetric, this means I have to have our good old friend sigma minus or the antisymmetric combinations of spin. So half my spin has to be up and half my spin has to be down at any given time. So one of the real questions that we should ask, since we've started talking about excited states, is what is my wave function going to look like for the helium atom once I go to the 1s1, 2s1 excited state? So how will my wave function change? So one of the first things we should really think about is going to be this spin component, because there's going to be two major ways I can combine my spins. Either my spins can be paired, and my spins will essentially still be pointing in the opposite direction like they have been for the ground state. So they'll be pointed exactly opposite to each other. Or, in comparison, they can be parallel, both pointed in the same direction, which will give me a net overall spin. So we're going to be talking about these two different cases today, and we're going to start with our good old friend paired spin that we've been addressing last week, before break. So we have, as we always do, special names for paired spins. So these are the same thing as being anti-parallel, because my two spins will always be pointed in the exact opposite direction, not just in terms of one being pointed up and one being pointed down, as we've been talking about, but it turns out they're also going to be pointed in opposite directions in the XY plane at all times. We can think about this as a way to make sure that they don't have the same spin at any given time, which will help guarantee the Pauli principle when they're occupying the same orbital. So what we're really going to want to focus on first, though, is going to be the orbital part. So I still have one electron occupying the 1s orbital and one electron occupying the 2s orbital. But now we have a pesky problem. Which electron is occupying which orbital? Is my first electron occupying the 1s orbital, or is my second electron occupying my 1s orbital? Well, as we addressed before break, it's both, because electrons are indistinguishable. So 50% of the time, which I get from a C1 of 1 over square root of 2, 50% of the time, the first electron will be occupying the 1s orbital, and the other 50% of the time, the second electron will, with corresponding the other electron occupying the 2s orbital. All right, so there we go. Should be fairly logical, just some pesky details of electron indistinguishability. Now, we have to also address what the wave function of the spin component looks like. So again, this is my old friend, sigma minus, where I have a 50% mixture of a spin being, the first electron being pointed spin up, and the second electron being pointed spin down, and then a 50% mixture of the first electron being pointed down and the second electron being pointed up. What this minus sign really is going to tell me is the fact that not only are they in opposite directions, but when this one is up, it's going to be pointed in the opposite direction of the one pointed down. Again, this helps make sure they're pointed in the opposite direction at all times. So hopefully that makes sense. Now, The last thing I really should bring in is the fact that not only are we caring about the spin of each electron, but it turns out we want to care about the overall spin as well, because it turns out the overall spin gives me magnetics. And some people turn out to care a lot about the magnetics of electrons. So the system will have a total spin angular momentum quantum number. Yes, I didn't have enough room for the full thing, of essentially the combination of the two spins. And since they're pointed in opposite direction, we'll take the difference. So the first electron has a spin of 1/2, second electron of 1/2, pointed in opposite directions. Lo and behold, my net spin is 0. And because my net spin is 0, guess what my net spin in the z direction is? It's also 0, which means that this system won't be seen by a magnet, because essentially there's going to be no net magnetic or angular momentum or magnetic moment in the z direction. So that's actually pretty cool and fairly useful feature of any singlet state, that they won't be seen by most magnets. Now, that brings us to the parallel spin, or as we call it, the triplet state. I'll talk more about where the name comes from later, but for now, you should just know that a triplet state refers to my spins aligning or being parallel. And so if my spins align, that means that the spin of my first electron and the spin of my second electron, instead of canceling out, will add together. And so we'll have a total spin angular momentum quantum number of 1. Now, one of the tricky things is how I can construct a spin. And it turns out there's one of 3 ways. The first way is probably the way you would expect. My first electron is pointed up, and my second electron is also pointed spin up. And so my 2 spins will add together, and I will have a net spin of 1. And it turns out that my total spin quantum number, or spin magnetic number, or m sub s, capital M, is going to be +1, because all of my spin magnetic moment is pointed up. So this means that the system will be aligned with a magnetic force that I apply to the system, which is a fairly useful feature. The next way I can combine my 2 spins into a triplet state is also fairly logical, though a little less intuitive. If they can both be pointed up, they can both be pointed down. So again, this way the spins build up. I'll have a net spin, all of it pointed in the down direction. So my spin magnetic moment is going to be -1. All right, so the only way I'm really going to be able to tell the difference between these 2 states is if I apply a magnet. Though it is worth noting that this will affect the degeneracy of my system, because I have one case where both the spins are pointed up and one where they're both pointed down, which means there's 2 different ways to get the same state or the same energy. An important thing to remember. Now, the third combination is actually very non-intuitive and sometimes can give some trouble. And that's the fact that I might have one spin pointed up and one spin pointed down. So first electron pointed up and the second electron pointed down. Or, of course, because of indistinguishability, the reverse. But it turns out that what this positive sign here denotes is that while I have the spins pointed in opposite directions, they're rotating in concert with each other, which means that they're always pointed in the same direction in the XY plane. And so while I have no net spin pointed up or down, so my m sub s is going to be 0, the spins still do add together, just entirely in the XY plane. So it turns out that this is a case where I can still get a total spin angular momentum quantum number of 1. And this essentially, again, comes from the two spins adding together pointed in the same direction. And so hopefully you see the importance of this sign. Being positive or negative tells us a lot about how these spins move with each other. Negative, always pointed in the opposite direction. Positive, always pointed in the same. And these are literally our two options. But it turns out that this sign has another very important feature. It means that all three of these triplet states have symmetric spins, which gives us some issues with Pauli, because the Pauli principle says that the total wave function has to be antisymmetric. None of my spins are antisymmetric. They're all symmetric to inversion, which means the orbitals themselves have to be antisymmetric. So I can take the spin components that I already had, either both up, both down, or moving together. And now the antisymmetry has to be in the orbitals themselves. So let's take, if both of my electrons are spin up, well, I can have my first electron in the 1s orbital and my second electron in the 2s orbital. But I can also have my second electron in the 1s orbital and my first electron in the 2s. But here's the real trick. I can't have my first electron in the 1s orbital at the same time my second electron is in the 1s. I have to make sure that these two are perfectly anti-aligned, because the Pauli principle says, guess what? I can't have electrons with the same spin in the same state at any time, ever. And that's really what adding these antisymmetric combinations of the orbitals really helps us account for. So I want to go ahead and just give a quick reminder. We can indeed have symmetric wave functions or symmetric spins, but if I do so, the wave function itself has to be antisymmetric, which again isn't possible if the electrons occupy the same state. So that's the reason why if I have a ground state helium where they're both in the 1s state, this guy will drop to 0. We can't ever occupy this state for a ground state helium, and only for the excited states. So once we go to an excited state, I can now occupy a triplet state. So let's see how many more times I can say the word state. At least once or twice, because we need to bring this back to how I got my singlet and triplet states and all of these excited states in general. I got these through electron excitation by a photon. And so let's take a look at the Gaussian diagram, or what allowed electron excitations we have for helium instead of hydrogen. So if I have helium, I start at a 2 electrons occupying the 1s state. Now, it turns out that when I do this electron excitation, my spins can't flip. Photons only are going to change the angular momentum of the electron, orbital angular momentum of the electron, not the spin angular momentum, because the spin angular momentum for an electron is always 1/2. So while I'm flipping my orbital angular momentum, the direction of the spin isn't allowed to move. So if I start in a singlet state, I have to go to a singlet state. No triplet states for you. So a 1s1 electron can only go, a singlet electron in the 1s state can only go to a singlet state with 1 electron in the p orbitals. It cannot go straight to the triplet state, which is slightly problematic because due to the fact that we have electron pairing energies, the triplet state, where I have 1 electron in the 1s orbital and 1 electron in the 2p orbital with same spins, is going to be favored by 0.8 electron volts. Again, this is that spin pairing energy. Electrons don't want to have paired spins because that means it's going to be easier for them to get close to each other and have greater electron repulsion. So, despite the fact that the triplet state is going to be energetically favored, I can't access it directly. So if I'm going to start in a helium ground state and end up in a triplet state, it has to be through excitation to the singlet state, and then after enough time, the electron relaxing into the triplet state. So this is a little bit beyond what we'll be talking about today, but it's important to know that it's out there as it informs a lot of spectroscopic techniques. The other thing I want to point out is that when I'm dealing with electron excitations, we're almost always talking about single electron excitations. Because energetically, if I were to try to excite both of my electrons out of my 1s orbital, that would actually take more energy than it would require to ionize the helium atom entirely. So going from helium to helium plus. So if I have to choose exciting 2 electrons or ionizing the system, getting rid of 1 electron entirely, you will always get rid of 1 electron entirely, which is slightly problematic for excited states, but makes it a much easier system to study, which we will take advantage of. So that pretty much brings us to the end of singlets and triplets for now. We'll revisit this topic later, but next up, we have to figure out how these spin states are actually going to interact with the energies of my orbital states, because it turns out that my spin angular momentum and my orbital angular momentum can interact. So we'll cover that topic next time. Take care and stay healthy.